Okay, so I will be giving the next talk. It's entitled Artificial Intelligence and Machine Learning in MR Angiography. So, as we just heard, machine learning promises to improve the entire workflow from acquisition to disease prognosis. So including sequence optimization and automatic scan planning at the acquisition level, a more robust and reproducible motion compensation and undersample reconstruction with extremely fast computational times, several types of imaging processing tasks, and quantification of imaging biomarkers based on which computer-aided diagnosis and prediction of treatment response and prognosis could be realized. So there are several studies that have recently shown the potential of machine learning for MRA, and most of them are still in the imaging processing arena, and I wanted to show you some examples here. So the first one is a deep learning approach that enables the automatic segmentation of cerebral aneurysms. And in this study, the authors performed acquisitions at 1.5 Tesla and 3 Tesla in 4 different sites. These are time-of-flight MRI acquisitions, and they show that they can improve the detection of the aneurysms in about 13% in comparison to the clinical detection. And hopefully you can see here there are some examples of aneurysms that they were detected by the network, but that they were missed by the radiologists. A second example in terms of segmentation of brain vessels is a modified unit that allows to segment large vessels with excellent quality and smaller vessels with good quality. And this approach outperformed the conventional graph cut segmentation. So again, on the bottom there, you can see the segmentation of the vessels in red and the errors with respect to the manual segmentation in blue and in green. And we can clearly see that the network-based segmentation is improving the segmentation with respect to the conventional one. A third example, also in terms of segmentation, is segmentation of phase contrast images to enable full automatic aortic flow quantification. Again, here the authors were able to show an excellent agreement between the machine learning segmentation and the manual segmentation. But the important part here is that the processing time, it was reduced to about 1 minute in comparison to about 12 hours that would have taken the manual segmentation for the entire data set. And as a different example, not in MRA, but in plaque imaging, this is radiomic analysis that has been done in T1-weighted images, black blood, before and after contrast. And this study has been able to show an improvement in the accuracy to discriminate between symptomatic and asymptomatic plaques. And this, therefore, is promising an imaging biomarker able to identify high-risk plaque characteristics. Now, this area is very interesting. However, in terms of quantification of imaging biomarkers, the literature is still very limited, and I wasn't able to find many more studies similar to this one. So in the rest of the talk, I would like to focus in another area that is showing promising results, slowly starting to come up. And the reason because I find this important is because this will affect all the rest of the workflow. So I will be talking about undersample MRI reconstruction. As a very brief summary, because Monica was describing this very nicely in the morning, MRI reconstruction is an inverse problem. So the forward problem is given by this equation, where the image that we want to reconstruct is X, E is the encoding matrix that incorporates all the information about the imaging process. So that means call sensitivity, Fourier transform, motion, and so on. And B is the sample data. Now, the trouble is that when we have undersample data here, this problem is difficult to solve. So we have to incorporate some regularization in order to stabilize the solution. So that means we are trying to incorporate some prior information about the image that we want to reconstruct. This, in terms of optimization, it can be written like this. So we have a data consistency term that enforces consistency between the acquired data and the model that we have about the imaging process, and the regularization term that incorporates the assumption about the image that we want to reconstruct. So in the case of compressed sensing, this regularization is an L1 norm, and the assumption is that the images are sparse or compressible. Now, why I'm showing you this? Because this type of optimization problem, it can be solved in an iterative way, and splitting the optimization into 2 simpler problems. So our first problems correspond to kind of like a denoising regularization, and the second one to a data consistency. So the idea is that this allows us to alternate between data consistency and denoising steps throughout the different iterations of the reconstruction. Now, this denoising, it can be exploiting sparsity, for example, in a given domain, let's say the wavelet domain, but it can also exploit sparsity in other domains or other type of sparsity, for example, the low rank structure of the data. So in that direction, we have recently proposed a 3D patch-based low-rank reconstruction that we call PROST. And the idea of PROST is to exploit the low-rank structure of a patch-based representation of the image. So the mathematical formulation is given by this. In very simple terms, we again can split this in two terms, a patch-based low-rank denoising and the L2 regularization that is using the denoised image as a prior. For the patch-based denoising, what we are doing is that we take a 3D patch in the image, then we search for similar patches within a neighborhood, and we put this information in a 2D matrix. So in the 2D matrix, we are exploiting local redundancies within each of these 3D patches, and non-local redundancies between similar patches within this neighborhood. Now, we can do a low-rank approximation of this matrix, so we can separate the patch-based representation of our image of interest from the noise-like artifacts that they were introduced due to aliasing. So then from this matrix, we can obtain a denoised version of the image that it can be used as a prior for the second step of the optimization. And we have applied this approach to reconstruct 3D whole hair images, both single contrast and multi-contrast. And here I'm just showing you an example. This is a non-contrast enhanced coronary MR angiography acquiring less than 10 minutes with 0.9 millimeter isotropic resolution. And I hope that you can agree with me that the quality is very promising in comparison with CT coronary angiography. So now this type of reconstruction, so compressed sensing type and also low rank, they can suffer from residual aliasing artifacts, low reconstruction times, and high dependency on the choice of the regularization parameters. So the recently proposed neural network-based method, on the other hand, they provide extremely fast reconstruction times after the training step, and they offer the option of learning the regularization, the parameters, and the transform from the data itself. So in very simple terms, the neural network-based reconstruction receives as an input the undersample case-space data or the alias image, and it produces as an output an image with minimum undersampling artifacts. So there are several approaches that they have been proposed for neural network image reconstruction. I will be talking about two of them today. The first one is image domain learning, and we can think of this one as performing only the denoising step of the iterative reconstruction I mentioned before, where we were alternating between denoising and data consistency. So in general, this approach doesn't include a data consistency term. So we will have a neural network that it will receive as an input an alias image, that it will have noise-like artifacts due to undersampling. And then the network, it will denoise that image to produce an output that it has a minimum remaining undersampling artifacts. A second approach is the so-called unroll or cascade network. And with this approach, the neural network is trying to unroll the iterative compressed sensing like reconstruction I mentioned before. So it's unrolling these denoising and data consistency steps. So we have an end-to-end network that alternates between neural network-based denoisings and data consistency steps through different stages. So in terms of image domain learning, the group in Northwestern University in Chicago have recently proposed a CNN-based method to accelerate the acquisition and the reconstruction of 3D respiratory resolve images. So this data is being acquired with a stack of stars in about 6-minute acquisition time. And before giving the data to the network, the data is being pre-processed. So the radial data is being beamed in different respiratory positions, gridded into the Cartesian positions, and then coil combined using sense. And it's this data, the coil combined time resolve, that is being given as an input to a CNN network that it has 4 layers. So we can see that the input actually is not the 3D time resolved volumes, but it's a 2D plus time plane of each of these volumes. This is a supervised learning approach, so the loss function is the L2 norm difference between, in this case, the grasp reconstruction of the same data and with respect to the CNN-generated data. And they applied this approach in 24 subjects, 10 for training and 14 for validation. And we can see here some of these results. So this was an abstract at the ISMRM. And I couldn't find the following publication, but hopefully it will be coming soon. You can see the very nice results of the CNN reconstruction in comparison with GRASP, not only in terms of the image quality, but also in terms of the quantification of the diameters of the different vessels. Now, importantly here, this reconstruction took about 75 seconds in a GPU, in comparison to 3.5 hours that take the GRASP reconstruction in a CPU. So this is basically one of the big advantages that we have with deep learning-based reconstruction. I quickly show you a second example. This is from Yonsei University in Korea. And they are applying this approach to speed up 3D time-of-flight brain MRA. And if you remember in the previous approach, it was some pre-processing of the data. So the data coming from the multiple coils was combined first with sense. But in that case, we are not exploiting the redundancies between the different coils. So with this approach, the authors are given to the network as an input, not the coil combined image, but each of the alias image coming from the different coils. So this is the input to a multi-stream network that extract features from each of the coils, which are then concatenated and given as an input to a second CNN network that will produce the sum of a square fully sampled image. So this is a network that is being trained end-to-end, and the loss function is basically the L2 norm difference between the sum of a square image and the undersample multi-coil images. So here, they are only reconstructing magnitude images, but they are not reconstructing phase data. They apply this to retrospectively undersampled data with different acceleration factors, with a Cartesian variable density Poisson sampling. And again, they show very nice results on the bottom for the proposed method by this group in comparison to the fully sampled image, much better than conventional parallel imaging techniques such as Saki and Spirit, and also outperforming conventional networks such as UNIT. And the important part here is that they are able to recover these small vessels that they were obscured due to undersampling. So just as an example of an unrolled network for undersample reconstruction, I wanted to talk about variational neural network. And if you remember, one of the problems of compressed sensing is, or the compressed sensing type of reconstructions, is that we need to choose the proper regularization term and an optimal regularization parameter. So we need to define before which will be this term and which will be the value of the regularization parameter. Now, if we think about this term in a generic way, this term can be defined as a function of potential functions, a sparsifier transform, and the regularization parameter itself. So the potential function, it can be the L1 norm or the L2 norm, and the sparsifier transform could be the wavelet transform. Now the problem is that we don't want to define that beforehand. So the idea of variational neural networks is that they can learn these optimal parameters and the transforms, and therefore the reconstruction from the data itself. So the network, it consists of several stages that they represent a gradient descent of each of these stages. The gradient descent is given by this expression where we can see the gradient of the data consistency term and of the regularization term. And if we look at the regularization term, which is basically this part, we see that the network consists of convolution with kernels, application of activation functions, and convolutions with kernels again. So what we need to learn from the network are the activation functions, the filter kernels, and the regularization parameters for each of the stages of the network. So this approach was proposed by Hammernin and colleagues originally and was applied to 2D knee images, showing very nice results. So we thought of extending this to enable motion-compensated 3D coronary MRA. However, in this case, we need to account for motion. So to account for respiratory motion, we use a previously proposed approach where we use image navigators to correct for bit-to-bit respiratory motion, and we use a variable density Cartesian undersampling to accelerate the scan. Now, importantly, we have to ensure in our case that the cardiac and the respiratory motion are identical between the input and the output during our training phase. So we are doing the training with retrospective undersampling data. And we are also proposing an extension, which is a multi-scale approach, because we need to capture the different spatial resolutions that they are visible in the coronary arteries. So this is just quickly the network that receives as an input the translational motion corrected case space. It uses a multi-scale approach for the magnitude image and a single scale for the phase, because we are assuming that the phase is smooth. And we applied this approach to 18 healthy subjects, 10 used for training and validation, and 8 of them used for testing and reconstruction, where prospective undersampling was done with 5-fold and 9-fold, and this was compared with fully sample acquisitions that they were done in a different scan. So here you can see some of our results on the top in the coronal view and on the bottom in a reformatted view. This is a 1.2 millimeter isotropic acquisition, 5-fold accelerated, performed in 4-minute scan time, and importantly reconstructed in only 14 seconds. So we can see that the VNN approach outperformed the compressed sensing and achieved a very good agreement with the fully sample scan that would have taken 19 minutes with 100% respiratory scan efficiency. And very similar results they are obtained if we accelerate even further to 9-fold acceleration, where now the scan is only about 2.5 minutes. So in summary, machine learning promises automatic patient-specific diagnostic, stratification, and prognosis. But for that, it requires an integrated approach from acquisition to clinical outcome. There are several recent studies that they have shown the potential of machine learning for MRA, but they concern mainly the image processing and more recently also the reconstruction steps. So importantly, in order that we can move forward in the workflow, we need harmonized acquisition and reconstruction, because these are fundamental to enable, for example, quantification of imaging biomarkers. And in terms of image reconstruction, there are different approaches that they have been proposed. Image domain learning and unrolled networks are only examples of them. But most of the ones that they have been proposed are supervised learning, so they require a reference. However, unsupervised learning may be needed to enable submillimeter acquisitions or acquisition with very high temporal resolution where the reference cannot be acquired. So an important advantage of this method is that they enable fast reconstruction, and that should facilitate clinical translation. However, there is a need for prospective validation and clinical studies. So thank you.